For you?
Yes.
Okay, thank you. Yes, so hello everybody. Apologies again that I'm also not in person, and apologies in advance if there are issues with my internet connection. It's been a little bit unstable this morning, so I hope this talk goes smoothly. So having had that nice introduction from Petra, I'm going to continue with gamma ray astronomy with Imaging Atmospheric Cherenkov Telescopes. So we already talked about water Cherenkov detectors. Essentially, we have this gamma ray interaction with the atmosphere, generating an extensive air shower. The water Cherenkov detectors will then sample the particles more directly, traveling through the water tanks. Imaging Atmospheric Cherenkov Telescopes then measure the Cherenkov light from the shower itself as the particles travel through the atmosphere. So we have detector arrays that can operate up to 24 hours a day. And IACTs are really restricted to just night only and preferably low moonlight conditions. So one of the key aspects of the technique is our ability to distinguish between gamma ray initiated and hadronic initiated extensive air showers. And so we talk about this gamma hadron separation. And there's been several key advances over the years. We started off with simple parameterization approaches such as Hillis parameters, which are mainly geometrical. And this then progressed into boosted decision trees, which have more or less become the standard for the field. And now people are diving into deep learning approaches, additional aspects such as muon tagging or event classes for the quality of the reconstruction that really enable us to further suppress the background and improve the performance of the technique. There are some limitations to this, however, so we're finding that neural networks can be highly sensitive to the environmental conditions of the experiment, and they could also be computationally expensive if you need to retrain the networks every time that the level of background light changes, so you have a different moon phase or a different region of the sky, or if the atmospheric conditions change. We do also have some limitations due to hadronic interaction models, simulation interaction model. At one example of a recent development, one as a tool for background work with recently is if you take some telescopes in an array to reconstruct the image, but not all of them, and you make a prediction for what the last telescope should see, you find that your prediction compared with the actual image, you sometimes see an additional component which is due to stray muons from the air shower, and this can be used to further reject events and improve the background rejection between, you see here the ratio between the gamma ray showers and the proton showers, and this has actually been applied to a few recent analyses already. An additional bonus of this is that we can measure the properties of muons in TeV air showers with IACTs. And why might we want to do that? It's because these hadronic interaction model uncertainties propagate through into the TeV range, where we also see variation in the muon flux between, say, 100 TeV protons, 1 TeV protons, and we see this variation between hadronic interaction models, also in other properties. So this aspect is also of interest for people working with IACTs. So if we come now also to, I also have a world map indicating the locations of current experiments, and I really wanted to highlight here mainly the locations of current major IACT experiments, which are these. And for the current generation, we have 3 major arrays. All of these, I should note, actually comprise more than one telescope. So this stereoscopic reconstruction of a shower with more than one telescope gives us a better directional reconstruction than just having one telescope on its own. So we have HESS in Namibia, which is comprised of 5 telescopes, 2 different sizes. We have MAGIC, which is 2 telescopes on the island of La Palma in Spain, and Veritas, which is 4 telescopes in Arizona in the US. And 2 sites are already chosen for the forthcoming Cherenkov telescope array, and there is activity starting on both of those sites with respect to the infrastructure for CTA. Is the CTA North, which will also be located on La Palma, and CTA South, which will be located near Parallel in Chile. And then just because we have a lot of overlapping gamma ray astronomy with our colleagues working with ground-based particle detectors, and we also show here HAWK, which is in Mexico, and LASO in China, and for completeness, the Fermi-Lat satellite. So these facilities use different techniques, but they do actually have complementary performance, and they have different strengths. So the left plot shows the sensitivity of various experiments, and the right plot the angular resolution. So we can highlight, this is how we expect IACTs to perform. I chose the CTA curve to show this, and we can compare this to the water Cherenkov detectors, and we see that they really do have an advantage, and particularly in collecting at the highest energies, at the cost of a higher energy threshold to their analysis. So the sensitivity is really much improved at the highest energies, but again, there's a bit of a cost in the angular resolution performance. We already heard from Petra that there are techniques being developed which are already showing improvements in the angular resolution, but in general what we do frequently see is a region that can be resolved into multiple sources by IACTs. The same region seen by a water Cherenkov detector becomes rather blurred and can even appear as a single source, which affects also how we count the sources. For completeness, you can also show the performance of the Fermi-Lat satellite, which can extend up to roughly 1 TeV in its energy reach. So if we look at the development of very high energy gamma ray astronomy over time, we started with just one source in 1989, the Crab Nebula seen by Whipple, which was just a single telescope, not stereoscopic. And this really pushed into the tens of sources with the advance of the stereoscopic technique and gradually increasing mirror area. So stereoscopy started with HEGRA, and then through to the current generation instruments, HESS, MAGIC, and Veritas, we really pushed this to more than 100 currently known very high energy gamma ray sources. I think it starts to get a bit ambiguous now as to how many sources we have. I think definitely over 200, but it's a bit ambiguous, the exact number, because many of these can be catalogued differently depending on the angular resolution of the instrument which measured them. But we certainly hope with CTA to push this into the thousands. Okay, if we look at the very high energy gamma ray sky, there should be two things that immediately jump out. The first is the galactic plane and the large number of sources concentrated along it. If you see that the grey points here, which correspond to the green here, the most popular type of source we detect is unidentified. So I think we still have a lot of work to try and work out what these sources actually are. In many cases, this could be because there's more than one counterpart, and so we're not quite sure which one is really responsible for the emission. In a few cases, we actually don't have any suitable multi-wavelength counterparts from which we can say, yes, this is the origin of the gamma ray emission. So there's still plenty of open questions here. The most popular type of identified galactic sources are pulsar nebulae or supernova remnants, or indeed composites, which are then a combination of the two. And we'll hear a bit more on those in a moment. And then we also have plenty of binary systems. When we look at the extragalactic sky, it should jump out that it's dominated by this red type. These are the same as this blue in the pie chart. And these are your active galactic nuclei, particularly blazars, where we're really looking directly down the jet. So blazars actually form a minority of the total number of active galactic nuclei known, but a majority of the sources detected at very high energy gamma rays, extragalactic sources that is. So it's really how it's boosting along the jet, and so there's really quite extreme systems. And the vast majority of the extragalactic sources are then different types of AGNs. We do have a couple of starburst galaxies and some GRBs, which have been detected in recent years. So looking at the galactic plane, just with HESS at the moment, you see that the coverage here is quite non-uniform. There is quite some variation in terms of coverage in the galactic latitude and in terms of depth and exposure. I just wanted to highlight some locations of currently known supernova remnants and pulsar wind nebulae, and then composite systems which seem to contain both a supernova remnant and a pulsar wind nebula, but we're not sure which is responsible for the emission. What I actually want to draw attention to with this is that this doesn't cover everything, and the majority of the remaining sources are unidentified, and this includes actually the galactic center, which is classified as an unidentified source because it is coincident with the location of Sagittarius A star. We don't yet understand the mechanism by which these very high energy gamma rays are produced, and so it is still an unidentified source. Okay, to highlight a few source classes individually, we can start with the Crab Nebula, which, being the first TeV source detected, has become more or less a standard candle for TeV gamma ray astronomy. It has, it's one of the highest energy sources known. There's been photons from the Crab Nebula seen by LASO extending up to 10 to the 15 electron volts, and one of the brightest, which led to the development of or the adoption, I should say, of crab units, which is a very arbitrary sense of how bright a very high energy gamma ray source is compared to the crab. Some recent studies that were done utilizing open source tools and common data formats have shown that you can combine data from multiple experiments to get sort of the best fit or the joint fit measurement of the crab spectrum. So you can see that the Fermi spectrum just extends to a bit over 1 TeV. We have Hawk, which extends up to 100 TeV or beyond, and then the current IACTs, current generations of covering the gap in the middle. So this joint fit approach, this is something that the field is gradually moving more and more towards, open data formats and sharing of data so that we can really combine data and do a multi-instrument fitting to gain a better understanding of the physics of the sources that we're studying. A couple of recent results on the Crab Nebula from Cherenkov telescopes. These include the measurement of the extension of the Crab Nebula, which is measured at 52 arc seconds. So this isn't an upper limit, this is really the size. And we can see how this compares to the X-ray torus of the pulsar. And also additional techniques which allow us to extend the reach up to 100 TeV. So using very large zenith angle observations, which was demonstrated by the MAGIC collaboration, this can be used to extend the spectrum measured from the crab up to 100 TeV in energy. So pulsar wind nebulae, these are the most numerous source class. Okay, this is maybe a bit inaccurate, saying the galaxy, in the very high energy gamma ray sky in the galaxy. I think we're probably outnumbered by blazars in the extragalactic sky. But just to compare a few different SEDs of famous or well-known pulsar wind nebulae, we have the crab extending to 10 to 15 electron volts. We have MSH 1552, which has a shape very similar to that of the crab in its SED, just reduced by a factor in flux. And this is the source on the left, where you see this coincidence between the gamma ray emission and the radio contours. This is also known as the Hand of God nebula. The crab itself is very pretty and optical. In gamma rays, it typically looks more like this right-hand plot. And I chose this plot to show as a point source, well, I should say similar to a point source, because it's actually from the SCT. Now, this is a telescope which uses dual mirror optics, which is another novel development for Cherenkov telescopes. And this dual mirror optics, which is foreseen for the Cherenkov telescope array, has also only really been proven within the last few years. So this is from 2020, this image. We also have the Vela X nebula, which is located very close to Earth. And so we see sort of a zoomed in view of the central part of the nebula. The gamma ray emission coincides very nicely with the X-ray contours, and we see a spectral maximum, which is closer to 10 TeV and really much higher than the spectral maximum of inverse Compton seen from other pulsar wind nebulae. So one more source that I'd like to highlight is SJ 1825-137. This is the canonical example of energy-dependent morphology, where what we see is electrons escaping, or rather traveling from the pulsar, traveling outwards and losing energy as they travel. And so the result is that you have a larger size at lower gamma ray energies, and towards higher gamma ray energies, the emission concentrates towards the pulsar, and the centroid also shifts back towards the pulsar. So we really know that the pulsar is responsible for the emission here. It's one of these complex fields of view where we also see two other gamma ray sources in the field, LS 5039, which Petro already mentioned. This is a gamma ray binary, and J 1826, which is another pulsar wind nebula just next door. A recent development is the identification of halos of escaped particles around accelerators, so specifically pulsar halos. And the canonical example of this is Gaminga, which was first identified at TeV energies using data from Hawk, the water Cherenkov detector. This is a larger field of view, which means it's less biased towards just seeing sources with a smaller angular size than the field of view. And so one of the questions is, why are we seeing these halos now? It's mainly from water Cherenkov detector developments. And indeed, the same study put some effort into improving the analysis sensitivity to extended sources. So we can see this is essentially compatible with what was seen in the map from the Hess Galactic Plane Survey before. And if we adapt the background techniques, making a few adjustments to make the approach for the analysis more similar to that used as standard at the time by Hawk, we see that we obtain a sky map which is much more similar. So we have two things here. The first is, sources that weren't previously identified pop out from the Hess data, And the second is that some regions which were well resolved actually become less well resolved in the HESS data. So there's pros and cons of using both approaches here. And by adapting some of the background analysis techniques, it was possible to show that extended emission around the Gaminga pulsar is also detected by IACTs. And you see the extreme extension compared with the PSF of the instrument. A recent result is, of course, that of the ultra-high energy sky above 100 TeV. 14 from seem to be associated with size, which we're really interested in remnants, perhaps.
Huh? Hello, Alison, can you hear me? I think you have connection problems. Can you go back about 30 seconds and maybe try to turn off your video? Maybe that helps.
Are we back? I think we were here when you lost me.
Yeah, one slide before, I think.
Ah,
Oh,
already.
this one,
So
it's
got
fine.
here.
No, you had it right
Okay.
the first time.
This one. Okay, good. So hopefully I won't drop out again. Let's see. Okay, hopefully this will stay stable for the remainder of the talk. So what you'd expect to see from leptonic accelerators is a Klein-Machine cutoff, so a very rapid cutoff, which is where you enter a scattering regime where the electrons lose a large fraction of their energy on each scattering interaction. What was recently shown, however, is that in high radiation environments, this cutoff can shift to higher energies. So it is still possible to explain the ultra-high energy spectra that we see from these sources of 100 TeV with leptonic emission. There are various candidates for the origins of cosmic rays at the beneath. These include stellar clusters. We have here HESS spectrum extending up to 100 TeV from Westerlund 1. I think this paper actually even appeared on the archive this morning. We also had the Boomerang Nebula, which was mentioned in the previous talk, where we see the highest energy gamma ray emission from this region from a different part of the source to where the supernova remnant is. So this could be an example of cosmic rays escaping from the accelerator and then interacting with clouds. We also have completely unidentified sources. So an example is HSJ 1702, where the highest energy emission, again, it reduces to just the location of this peak, this green circle, but we don't have any counterparts. So it's still open what the origin of this source is. Okay, we also have binary systems, so several different types of gamma ray emitting binaries. These include colliding wind binaries, such as Eta Carina, which has a period of 5.5 years, and we observe gamma ray emission corresponding to the time of its closest approach, so the periastron. We have gamma ray binaries, which have a wide range of periods. We have LS 5039, which has a period of just 4 days, and recently gamma ray emission shown from the periastron of the system containing the pulsar J2032. This has a period of 50 years. So there's really a wide range of periods in these binary systems and everything in between, including this. And recently microquasars. So these jets from SS433, which were detected by HAWK and recently confirmed by HESS, that we also see with IACTs, very high energy emission from the jets around this microquasar. Another type of binary system recently established in very high energy gamma rays is novae. And the first nova to be detected in very high energy gamma rays is RSF UT, which is a binary system comprised of a white dwarf and a red giant. at notionally 1.4 kiloparsecs, but there are arguments of why we might think it's located a bit further than that. Semi-regular explosions have been observed from this system since 1898, and the most recent two were in 2006 and on the 8th of August last year, so almost a year ago now, reaching a visual magnitude of 4.6, whereas in the quiet state it's just at 12.5. And this during this outburst, very high gamma emission was actually detected by all of the operating Cherenkov telescopes. Unfortunately, Veritas had a seasonal shutdown at that time. And in this case, we see the very high gamma emission extending over several days, and even up to a few weeks later, there was still some signal from this system. And in both interpretations, the hadronic scenario is in general preferred for the acceleration here. Okay, keeping with the theme of transients, in recent years, we also had the first detections of gamma ray bursts from HESS and MAGIC. So between 2018 and 2020 so far, they're all long GRBs during the afterglow phase, and there were two really exceptional ones. The first is the first GRB to be detected at more than a redshift of 1 at 1.1, had an extremely high energy output. And the second is the closest GRB detected to a redshift of 0.08. And this was detected over 3 nights by HESS, so going from over 20 sigma on the first night to just about 3 sigma on the third. And so the question is, why are we just seeing GRBs now? Well, there were several improvements in the response time of Cherenkov telescopes. But additionally, there's an intrinsic challenge. So for large distances, which is the majority of GRBs at redshifts greater than 1, there is some severe attenuation due to the extragalactic background light, which absorbs photons through the interactions with the EBL on their path to Earth, and this leads to strongly attenuated spectra that can be sufficiently attenuated that they no longer extend into the very high energy regime. So keeping with an extragalactic theme, the majority of extragalactic sources are indeed blazars. The first indication of a neutrino source with one of these came from TXS 0506 at a redshift of 0.3. And there was associated with this IceCube event, IceCube alert, there was gamma ray detection of flaring activity by both Fermi-Lat and MAGIC, and a chance coincidence was then disfavored at roughly the 3 sigma level, which is a nice indication that we are entering this multi-messenger astronomy era. And indeed, in a look-back analysis, they also found previous examples of or candidate events from this region of the sky with IceCube, leading to a 3.5 sigma hint that this has been going on for longer than just this recent flare. The first alert from a CTA telescope, so from this prototype LST, which is currently in commissioning on La Palma, was the detection of flaring activity from a blazar via Lacate, and I think this was in 2021. This was announced, and a recent result on the radio galaxy Centaurus A was resolving the extension of the jets, which has been resolved to have the size of at least 2.2 kiloparsecs. Okay. On to
Alison?
briefly fundamental physics.
Alison, we have 5 minutes, please.
Okay. On to fundamental physics. So we have, we can also place upper limits on dark matter. So this is using the indirect search approach. So we expect to have dark matter annihilation producing photons. We can place upper limits from observations of dwarf spheroidal galaxies, and it was shown at Gamma 2022 this year that a combined limit, really again combining this data from multiple instruments, gives us a more constraining result. So the combined likelihood over observations from multiple instruments gives us a most constraining upper limit. And there are other candidates that we're going to look for signatures from, such as axions, and these would then modify the gamma ray spectrum. So in principle, axions allow you to escape some of the EBL effect, and this would lead to an additional bump in the spectral energy distribution at the highest energies, where you become less attenuated from the EBL than you would otherwise be, due to the photons transforming into axions along their journey through the universe. And so just one of the last things I wanted to cover is the cosmic ray electron spectrum. And this is because recent results using gamma rays have shown that for a few accelerator systems, we have slowed fusion in the vicinity of an accelerator. So the cosmic rays generate their own turbulence, and some self-generated confinement occurs, which really slows down the diffusion. And this leads to a challenge in explaining the cosmic ray electron spectrum. I really wanted to highlight that the electron spectrum measurement is extended at the highest energies purely by Cherenkov telescopes. So it's not just the cameras, but also we can reconstruct the electron spectrum. And this leads to a challenge to explain and to reconcile the two, this slow diffusion and this high energy cosmic ray electron spectrum. And most arguments, less popular, a dark matter scenario is less popular these days. People look more for a local source, so like a local supernova element or a local pulsar. And coming back to these hadronic interaction model uncertainties, this actually gives us an uncertainty in the energy scale of plus minus 15% due to these uncertainties. So just to conclude with some outlook, what I really wanted to highlight by mainly focusing on recent results is that even though it's been over a decade of operation and coming into 2 decades for the current generation of IACTs, discoveries continue to be made. And this includes even new source classes occurring at TeV energies. And the forthcoming IACT facilities, we have CTA North, La Palma in Spain, and this is an image of the LST currently located on La Palma. We have CTA South in Paranal, Chile. So this is actually located in the valley between Cerro Paranal, which is the mountain with the BLT on top, and Amazonas, so really in the valley between the two. And there's also the forthcoming astronomy around Tenerife. And ground-based water Cherenkov detectors have produced some impressive results in the recent years, and they are continuing to really push the field towards the highest energies and full sky surveys. And meanwhile, IACTs can really focus on their complementary strengths. So this is really the good angular and energy resolution and the capability for detailed studies of these sources, as well as the reaction sensitivity to transient phenomena, particularly with a lower energy threshold. So look forward to many interesting results and discussions at this Cosmic Ray Symposium. So thank you, and apologies for dropping out briefly.
Okay, thank you very much, Alison. I think I'm sorry we are already late, so we have to move for lunch. That is also an important activity of the conference. So I give some announcements.
Okay, thanks. Well, we can be quick. Oh, can I still see something?